professor to actually not show you that, to show how we bring everything together into one problem. So I'm going to do something that's going to just be a very basic problem though. So we're going to do those two things, then we're going to move on to the next topic, which is optimization. All right, so recall from college algebra that if you're given a function f of x equals ax squared plus bx plus c, that we know that if a is a positive number, that this parabola will open upward, right? And we know that if a is negative, that this parabola will open downward, right? And in both of these cases, that point right here, hk, hk, this one right here, hk, is called the vertex, right? This vertex is that point hk. And in college algebra, you're given a formula. You're told that h is equal to negative b over 2a. And then to get k, you're told to take that answer and just plug it into your function, and that'll give you k. Well, let's see where this formula actually comes from. I mean, you're given that formula in algebra, and then you just accept it and take it on faith and everything else, right? So let's see that this formula is actually a gift from calculus, all right? And the idea is this. A parabola, regardless of whether or not it opens up or down, it's going to have either a minimum or a maximum, right? And since a parabola looks like that U shape, it's only going to have one local max or one local min, right? Depending on the two cases. So you can have one local min or one local max. So if I were to just kind of back up and give you the parabola in a generic form like that, and ask you to go tell me where this goes up and down, or go find where you have the derivative, like any critical numbers, right? You would first take the derivative of that, right? Take derivative, what would you get? Remember, a, b, and c are constants. So what would you get if you take derivative right there? 2ax, right, plus b, right? And that's it. That's all you'd get, right? So that would be the derivative. And now you'd find the critical numbers. So you take that derivative and you would do what with it? Figure out where it's 0, right? And then figure out where it does not exist. But we don't have to worry about does not exist because that's a polynomial, so it's never going to not exist. But setting it equal to 0, you get what? You're solving for x. What do you get if you solve that for x? Subtract b on both sides and divide by 2a, and you get negative b over 2a, don't you? And we know that then if you go to the number line and you put that there, negative b over 2a, partition it, take your two test points, you're going to figure out that it either goes up and down or down and up. And we know it has to do one of those two, right? Because it's a parabola. So that's why in your college algebra class they say, hey, if you want to find that vertex, guaranteed, it's going to happen here. It just comes from that simple idea. Does that make sense to you? Okay, that's it. I just want to show you that. That's where that formula comes from. All right, now let's do an actual example. And I'm going to bring up the notes to show you what we're not going to be doing. Curve sketching, all right? So when it comes to sketching a function by hand without the assistance of a graphing calculator or a computer, this is the actual set of steps that people would do back in the day, all right? You're given a function and you're said, hey, go sketch this thing. First thing you would do is you'd find the domain of the function. Then you'd find any x and y intercepts. Then you'd check for symmetry. You'd look for any asymptotes. Steps 1 through 4 are all college algebra ideas. Then you get to calculus. Figure out where it's going up and down. Go find local maxes and mins. Figure out where it's concave up and concave down. Figure out where you have inflection points. And then you draw it. All right? So I'm going to take you through one simple problem following all those steps. So I'll refer back to these steps. So here's the instructions. I want us to sketch f of x equals x to the fourth minus 4x squared. Oops, 4x squared. Keeping it simple. That's going to be easy to differentiate. It's going to be easy to set it equal to 0, so we should be able to move pretty quickly through this. So I want to sketch this. First thing I'm going to do is I'm going to talk about its domain. What's the domain of this function? All real numbers. So when I graph this, the graph should go in both directions forever, right? That's the first thing. Second thing, I'll go in the order here. Find any x and y intercepts. So this is the first thing. Second thing, let's find x and y intercepts. Well, how do we find x intercepts of any function? Take the function and set it equal to 0, right? Figure out where that function's 0. So we take the function x to the fourth minus 4x squared. We set it equal to 0. What can we do here? GCF? Greatest common factor? Pull out x squared. I'm left with x squared minus 4. Does that factor anymore? Yes, difference of squares. Yep. So x squared, x plus 2x minus 2 equals 0. And then get your, what, 3 x-intercepts? 0, -2, and 2. You with me? So I know where this graph hits the x-axis. Let's find any y-intercepts. How do you find y-intercepts for any function? Plug 0 in for the x, right? And what happens if I plug 0 into that function? I get 0. Okay. So look, this is, over on this side, I'm going to do this. It's not going to be my final picture, but it's just to give you an idea of what we've figured out so far. We figured out that if you draw this function, this is what it looks like, right? It's got these, it's got those 3 x-intercepts, right? And that point is actually the y-intercept as well, all right? That's what we figured out so far. Okay, now the next thing we do. We check for symmetry is step 3. Check for symmetry. And to check for symmetry, what that means is I need to see if this function is even or odd. This again goes back to a college algebra idea. So for symmetry, I'm going to ask, is this an even function? Is it an odd function? So how do we check for even? You, again, have to go back to college algebra for this. To check for even function, what you're looking for is you're saying, is f of x equal to f of negative x? In other words, if I plug a positive number in there, do I get the same thing as plugging a negative number in there? Do you get the same output? Well, let's check. What happens if I plug x into this? Well, you get exactly that, don't you? So this side is, I'm going to move it down here, is x to the fourth minus 4x squared. The question is that equal to plugging a negative x into it? What do y'all think? Do you get the same answer? Yeah, because if you take a negative number raised to the fourth power, the negative doesn't matter anymore, does it? And if I take a negative number and square it, it doesn't matter. So this side actually becomes x to the fourth minus 4x squared again, and these two are exactly the same, aren't they? Now, if this would have been like x cubed, then they wouldn't be the same, would they? So because they're the same, they're even. And what does that mean when you have an even function? When you graph it, what can you say? Do you remember? It's a reflection of itself on the y-axis. So that means that whenever I draw this, whatever I draw over here, it should be a mirror image of itself over here. You should be able to reflect it and get the same thing. Now, I'm not going to go through and talk about, when you have a function, it can only be even or odd or neither. It can't be even and odd. So I don't need to check for odd. But does anyone remember what you do to check for odd? Like if it hadn't been even, what you check? You have to see if f of negative x equals negative f of x. In other words, you're checking to see that when you plug a negative in, do you get the same thing as the function but with a negative in front of it? And you would check that. And if it doesn't match up, then it wouldn't be odd. And if it was odd, it's symmetric on the origin, which really means it's a double reflection of itself. It's like odd means, this is an example of an odd function. If you reflect this over and then reflect that down, you get itself. That's odd. Even would be like a parabola. Even, odd. Okay, so I've figured out that it's even, right? That's just going to be helpful when I draw this thing. The next thing I would do, find any asymptotes. Find any asymptotes. There's a lot to this part. Well, not a lot, but there's a lot of things to consider, all right? What type of asymptotes can we have? So let's see, asymptotes, I'm going to put asymptote just like that. So let's first talk about vertical asymptotes. Vertical asymptotes. So for vertical asymptotes, what we would have to have is we would have to have a situation that we've seen in this class where the numerator is fixed and the denominator goes to 0. Remember that when we did a limit like that? When the numerator was fixed, denominator went to 0, went to infinity, and that's where we had vertical asymptotes. Here we won't have that because the original function isn't even a fraction, right? So we are not going to have any of these. But horizontal asymptote, that we do need to check. And to check that, what we need to do are two limits. The horizontal asymptote is telling me what's happening as I go out to the edges forever. So if I go out to the right forever, what is my graph doing? If I go out to the left, what is my graph doing? So first thing I'm going to do, take the limit as x goes to infinity of this function. And then I need to go the other direction to the left side of the x-axis, negative infinity of this function. And these are going to be pretty clean, I think you'll agree. They're both infinity. Why is the first one infinity? Aren't you getting infinity minus infinity? How do you deal with infinity minus infinity? Two ways you can look at this. You could say that exponent's bigger than that one, so this one should dominate. Or you can do a GCF. I'm going to do just GCF because I think it makes it a lot easier to see. If I pull out my GCF, now what happens is as x goes to infinity, that's infinity, but now times infinity minus 4 is still infinity. So you have infinity times infinity, which should be infinity. What is that telling me is happening? As I go out to the right, where's my graph going? Up. So I should expect to see my graph go up on the right-hand side. Okay? Similarly, on this one, if I do a GCF, go to negative infinity out the left side, I still pull out that GCF, and it changes nothing because when I take negative infinity and square it, I get positive infinity. Negative infinity squared, I get positive infinity. Take 4 away from it, it's still infinitely big. 2 infinities multiplied together is infinity. So you know the left side goes up as well, right? We could have already said that with the symmetry, couldn't we have? Like whatever this side does, the other side does. But this just shows it, all right? All right, everything we've done there is algebra. You know, well, the limit's not algebra, but those are the concepts from algebra. These horizontal, vertical asymptotes, intercepts, right? That's all algebra. Now we come in, we bring the calculus in. So what we're going to do now is we're going to determine where it's going up and down, local max, local min, all that stuff, right? Concave up, concave down. So I'm just basically going to do what we just did in this class on this function. So step 5, let me see where this function's going up, where it's going down, right? Any max, mins. So what am I going to need to do this step? What am I going to need to work with? The derivative, right? So I may as well take it. Take the derivative. 4x cubed minus 8x to the first power, right? What am I going to do with that derivative? Figure out where it's 0, figure out where it doesn't exist, right? So where's this thing 0? Well, set it equal to 0. Let's pull a GCF out. I'm moving quickly. So I set that equal to 0 and I pulled a GCF, yes? Set those each equal to 0. Can anyone tell me what my what my 3 solutions are? 0, plus or minus root 2. So there are a couple ways you can do that. You can just set that to 0 and then set that to 0, move the 2 over, take the square root on both sides. You get 3 answers. Do I need to look at where it doesn't exist? No, because it's a polynomial, right? Okay, so now what? Yeah, we're going to need test points. So put those answers on a number line. That breaks our number line into 4 regions. I need 4 test points. -2, -2, -1, -2, -1, 1, and 2. Are you all right? I know I'm going fast. That's why it's recorded. Yes?
Couldn't we use the second derivative instead of having to check points in the first derivative?
Use the second derivative for, I don't know how you mean use the second.
Maximum and minimum.
I'm not, so there's something called the second derivative test where you use the first and second derivative together to figure out max and mins. I don't know if that's what you're referring to, but we're trying to figure out where it goes up and down. So I'm not sure you would be able to determine all of that with just the second derivative. Can you explain more of how you are intending on doing it? I don't want to tell you, I don't want to say no, but I mean, I don't know how we could, it sounds like you're saying, is there a way we can like not do this step? Is that what you're saying? Or,
yes.
Okay, how would you do that though? Will you think about it?
Like, if we know that, let's say from 0 to negative infinity, it's concave up, just for example, right?
Uh-huh.
Then couldn't we say that at the negative square root of 2, it's a local minimum, meaning that to the left of it, it would have to be it would have to be decreasing, and to the right of it, it would have to be increasing.
So you're saying if you're concave up, say at root 2, just say it again. Say at root 2, you find out that at root 2 you're concave up. Yes?
Yes, that means that to the left of it, it would have to be decreasing, and to the right of it, you would have to be increasing.
But concave up doesn't mean that it has to look like the entire smile. It could look like just part of it. Maybe that's where the confusion is. Because if I say that something is, are you saying I think what you're referring to is a second derivative test. There's an actual test where you go to this critical point, you figure out that the derivative there is 0, and then you show it's concave up, and then you can say it's a local minimum. Is that's what you're referring to?
I believe so.
Yes, okay, so that's a specific test that I have not shown. At this point, I have not shown that test. So you're asking to use something that I haven't shown yet. So the answer is yes, but generally speaking, I can't say that we're going to do that because I haven't shown you how to do it yet. Okay? All right, so back here, we're going to test these points, right? I don't feel like testing them, so I'm just going to say what they do, right? Should go down, then what do y'all think it does? Up? How do I know that? How do I know that part? Remember we did the right side we said should go up? Right, and by the symmetry, the other side should go up, which means it's going to go down then up. Okay, so I really just need to check one of these. Let me just plug 1 into this derivative. If I plug in 1, what do I get? Plugging 1 into this derivative right here. 4 take away 8. It's negative, right? So it's down. What happens when you plug in -1? Is it down? -1 right here is -1 times 4 is -4, but then the double negative would be +8. So it should be up. Like that. All right, so we've got that, yes? You see where we have a local min? Right? Local min, local max, local min. I'm not going to write them down. I'm just going to keep going. All right, now let's look at the second derivative. What's the second derivative of this function? 12x squared minus 8. All right, we want to know where that second derivative is positive and negative. Well, where it's 0 first. So set it equal to 0. What do we get there? Square root of 2/3, plus or minus. You'll know what I'm doing here? I'm looking for concavity now. So I'm looking at the second derivative. I'm figuring out where that second derivative is 0, solving, getting two solutions. Where's the second derivative not exist? Does it not exist? All real numbers, right? So we only have root 2 over 3 and negative root 2 over 3. Oops, 2 over 3. And so I pick a couple of test points here. 0 is a good one in the middle. And then 1 and negative 1. And those numbers are getting plugged into second derivative, which is right here. You plug negative 1 in there, what do you get? Plug negative 1 in there, what do you get? Positive. So that means we are concave up here, right? And 0 in there, you get negative. So that means our function's concave down. And then 1, we get positive, we're concave up. Okay, now I know I've moved fast through that, but is everyone okay with it? Everyone follow? This is the step where we have to bring it all together now, all right? We're done with all, we can tell by looking at this where local max, local min is. We can see from that any inflection points we have, right? We have 2 inflections, don't we? Here and here. So now, here's the way that I usually in the past have taught how to do this final step of drawing the picture, all right? And this step is, well, I guess when I was a student, this is not the way I learned it. I learned it most textbooks use this thing called a sign chart, but I'm going to do it the way that makes sense to me and the way I teach it, which is this. I'm going to start off by drawing a number line. And leave yourself space below this. You're going to need some space. On this number line, I'm going to first start off by plotting everything that I have in terms of my x-axis, my x-intercepts, and my critical numbers from both this step and this step. So what were my x-intercepts? 0 and 2 and negative 2, right? I'm going to put those there. My critical numbers were positive negative root 2 here, which is going to be somewhere in here, root 2, negative root 2. And then these two, right? These two. Oh, I'm missing 0. Well, 0's already in there, right? That 0's already there? Okay, and then positive and negative root 2/3 is in here. And I'm not trying to get it perfect. I'm just trying to make sure that they're in the right order. Okay, those are all my important points, right, from this problem? From this, I'm going to make a table. And I want to highlight something for you here. The things in red are the things that came from the derivatives, right? Everything in red came from the derivatives. So from where I have that, I'm going to make a table above this, like this. I'm ignoring the 2's because the 2's are my x-intercepts. I'm going to make a table here, just like that. Oh, it's supposed to have 3 rows, sorry. All right, so from only the critical numbers that I got from the first and second derivative, I'm drawing vertical lines. And then I draw 2 horizontal lines, so I have 3 rows. And what I'm going to do now is put all this information together. So this first row is going to be information about the first derivative. The second row is information about the second derivative. And the top row is information about the graph f itself. If you're confused, just let me keep going, all right? Let's talk about the first derivative, this row right here. What do we know about the first derivative? It tells us our function is going to go down until I get to where? Negative root 2. So to the left of negative root 2, I'm going to put an arrow pointing down. And then it's going to go up between negative root 2 and what? 0, right? From here to here, it goes up. Up in both of those little boxes. Do you see that? To the left of negative root 2, I'm going down. Between negative root 2 and 0, I'm going up. And then from 0 to root 2, I'm going what? Down. So from 0 to root 2, I'm going down. And then once I get past root 2, I'm going up. Okay, you see that? Now let's look at the second derivative. To the left of negative root 2 over 3, I'm what? Concave up. Here's negative root 2 over 3, right here. To the left of that, I'm concave up. So I'm concave up, concave up. Between negative root 2 over 3 and positive 2 root over 3, I'm what? Concave down. That's between these two, I'm concave down in both of those blocks. And then once I get past that positive root 2 over 3, I'm concave up the rest of the way. That okay? Final step before I draw the picture is I'm going to use both of these pieces of information right here to draw what the function actually looks like. So if I tell you that you have to look like a smile, but at the same time you have to be going down, that means you have to look like the left side of that smile, right? Like this, right? Because if you're on the right side of the smile, aren't you going to be going up? We have to be going down on a smile. So that means you have to look like the left side of it. And then on this section, I have between here and here, I have to look like a smile, but I have to be going up. So which side of the smile does it have to look like? The right side. So it has to look like this. And now I have to be going up a frown. How can you go up a frown? Left side of it, right? Left side. So it has to look like this. And then you have to be going down the frown, which means it has to look like the right side. And then it has to be down the smile, so which side? Left side. And then you have to be going up a smile, which means you have to be going up the right side. See, what we've just done is we put all the calculus together to tell us exactly the shape of our graph in each of these sections. And now all we have to do is put it all together in a final picture. Questions? I'm almost done. Here comes my final graph. Right below this, I'm going to draw my graph. And I'm just going to carry down 0 here. That's my y-axis. Here's my x-axis. And I'm going to bring everything down. So root 2 over 3, root 2, 2, negative root 2 over 3, root 2, negative root 2, and negative 2. Let's go to the very beginning. We had x-intercepts, didn't we? These points lived on our graph. Here comes my final picture. I have these x-intercepts that I found, right? They were there, there, and there, right? Now, to get the rest of the picture, what I'm going to do is I'm going to plug these values into the original function. Could you not do that? Plug those in to the original function and get y values? You could, yes? Let's just do this one. Let's do the positive one. What if I took root 2 and plugged it into the original function? What's f of root 2? Remember the function was x, it was x squared minus 4x, wait, it was x to the 4th, so it's going to be square root of 2 to the 4th minus 4 times the square root of 2 squared. What's that? What's root 2 times root 2 times root 2 times root 2? 4. Minus root 2 squared is 2, so take away 8. You get negative 4, you get negative 4. So down here, I'd be at negative 4. Do y'all see what I'm doing? And then I could plug in root 2 over 3 into there and get a point. Let's do it right here. F of root 2 over 3 would be root 2 over 3 to the 4th minus 4 times root 2 over 3 squared. The first one is 4/9 minus, and then over here when you square that you get 2/3, and multiply it by 4 you get minus 8/3. Common denominator. Multiply top and bottom by 3, so 24 over 3. What does that turn out to be? Negative 20 over 3? Which is about what, roughly? Oh, why did I put 3? Sorry, thank you. 29ths. What is that about? Negative 1 point something, right? Or negative 2 points, sorry, negative 2 point something. Which means I'm about where? I don't know. We're just going to eyeball it. Right about there? Now, I'm not going to plug the other ones in. The reason why is because I know there's symmetry here, right? Whatever happens here, happens here. So I'm ready to put it all together with my final thing. I keep saying that. I'm ready to put it all together. Because it's an even function. Symmetry over the y-axis. If there was no symmetry, I'd have to plug in all these numbers. All right, so let's connect these two dots. Let's connect these two dots together. When I connect them, I'm going to look up here and I'm going to see what it's supposed to look like. It's supposed to look like this, right? So I'm going to draw it like that. It's going to be concave down and decreasing like this. And then between here and here, it's going to be this. Left side, concave up. It's going to look like this. See, that's a what right there? That point is a inflection point, right? That's an inflection point. And then from here to here, between these two, it looks like what? Root 2 to 2? It looks like that, right? Right? Between here and here, it looks like that. So it's going to go like this. And then what happens now? I just keep going up. Why? Because we knew from the asymptotes thing that the right side was going to go up forever. And now the other side is just a mirror image of this, like a reflection. So this point here is here, this point here is here, and then it does the same thing. It's mirrored image, so it's, it matches this right here. That, and then this one goes like this, and this one goes up forever like that. And that is a very accurate in terms of